Hey guys, cool. So in today's video, we're checking out the grade 12, June 2025 science paper 1 paper. So this is the physics paper and we are jumping into question 1, the multiple choice questions. There's always multiple choice questions in the beginning with 20 marks, quite a few marks in the grand scheme of things, but it can go pretty quickly provided we understand which type of questions they usually ask, usually some sort of definition type questions, and then from there, formula manipulation questions as well as interpretation. Cool. So let's check out 1.1. So 1.1, which of the following forces always acts perpendicular to the surface on which a body is placed? So a body is placed on a surface. Which of the forces acts perpendicular to the surface, okay, at a right angle? So we're just trying to break it down before we check the options. At this stage, A is tension, B is frictional force, C is normal force, D is gravitational force. So our answer is C over here, normal force, because the Fn always acts perpendicular to the surface. We're going to see why it isn't A, B, and D. If it was tension or an applied force, it would be pulled on the object, tension being some sort of string or rope attached to the object. An applied force can also be through the means of tension. A frictional force would oppose the motion of the object, cool, and then gravitational force would act down to the center of the earth. So therefore our answer is C, and that is our first 2 marks. 1.2, it says a car of mass m moves along a straight line at a constant velocity of v. We have a constant velocity of v over there in an easterly direction. The velocity of the car decreases to 1/3 of its original speed, to 1/3 of its original speed in t seconds over here. As shown below, the graph is not drawn to scale. Okay, so this is a velocity time graph. We have velocity on the left there, we have time on the right here, and then it says what will be the change in momentum of the car. Okay, so we have a couple options here. We will read them just now, but what we first want to see is the formula that we're working with. The first question didn't require a formula, it required understanding of some Newton's theory, but over here it is requiring us to understand that change in momentum is this formula over here. So delta P is the change in momentum. It is the mass times final velocity minus the mass times initial velocity. So if we bring it back to here, what we're dealing with is m. It is the same mass, so we can factorize that out with the final velocity minus the initial velocity. So that means at this stage we can just go ahead and we can plug in our final velocity, our 1/3v, and our initial velocity v over there. Because mass is mass, they told us this. Final velocity is 1/3v. Our initial velocity is just v, which means it is 1v. And then we can go ahead and we can solve for it. So m is here. 1/3 minus 1 is minus 2/3v. And therefore we have minus 2/3m times v. Just multiplying these all together, putting it in a format that is similar to the multiple choice options that we have. One thing that's important with the change in momentum is that if ever we have a negative, it means it is opposing the initial direction, which means we were initially going east. So if we were just to remove our negative, we would say therefore 2/3mv to the west, because the negative is implying the opposite direction. So the change in momentum of the car, we have A, 1/3mv east, we have B, 1/3mv west, we have C, 2/3mv east. Okay, that's close, but it's not what we have. And then D, 2/3mv west, and that is what we calculated here by understanding which formula we're working with, and therefore our final answer here is D. So 1.3, object Y exerts a gravitational force of 1,000 newtons on object Z when the distance between the centers of the two objects is r. The two objects each have a mass of m. Which of the changes below will increase the gravitational force to 4,000 newtons? So we have a couple options, but what we need to do first is see which formula are we working with. So at this stage, I didn't copy over the formula sheet for that one, but we are working with this guy over here. The force equals the gravitational constant, that should be a capital G, multiplied by the mass of the two objects over the radius squared. So I'm just going to bring that over here and we can plug it in, and then we can start to interpret what change we can make in order to move this 1,000 newtons or turn it into 4,000 newtons. So at this stage, I'm just going to plug in everything so we can start to interpret. So our force is 1,000 newtons. Okay, our gravitational constant we don't need in this situation when we are working with some sort of theory changes over here, because as we see, what we're trying to do is double the distance between their centers or halve the distance distance between their centers, or halve the mass of both objects, or double the mass of only object y over here. So we're trying to see what change we can make in theory that can just affect our final force, which means any gravitational constants we usually don't need in these sort of questions, as they would be the same in both situations. So what I'm going to do is go m times by m, because they told us the mass of the two objects is m, and then at this stage we had our distance between their centers, which is r. So that is r, and then that is squared always as per our formula. So what we need to do now is simplify this a little bit. So m times m is m squared over r squared. So now we can start to approach each section to see what is happening. It makes sense in these questions to look at the radius first, and then we can compare the masses. So what we're going to do here, we're going to check doubling the distance between their centers. One other thing to note is that what we're trying to do is we're trying to increase this 1,000 to 4,000 over here. So if we are trying to increase this, the only two options we have is to either increase the mass of the object or decrease the radius, because the force is directly proportional to the mass of the objects and inversely proportional to the distance between them. So the bigger the masses, the bigger the forces, or the smaller the radius, the bigger the force. So that means we're looking at two options. Doubling the mass of only the object, that could work. Half the mass of both the objects, that won't work, because that would make the masses smaller. If we make the masses smaller, this will get smaller, so that one's out. Halving the distance between the centers, that could work. A smaller value here means this value will go up. And then doubling the distance between their centers means the distance between this and that will be further away, which means this is a bigger number, which means that this goes up, this guy goes down over there. So that means A is out. Okay, and at this stage we can just go ahead and look at the radius first as a process of elimination, as that is the most common thing in these sort of questions. So what this means is we're going to now plug in this variation they're asking to see if it does give us the 4,000 over there. So halving the distance between their centers. So if we go m squared over half r brackets squared is 1,000 over here. What we do is we square both of these, which means we get m squared, that stays the same, over 1 over 4, and the r squared is also there. And then we have 1,000 over there. Okay, once we've done this, we can go ahead and we can simplify the divided by 1 over 4, because if we tip and times this, it's like saying 4 over 1. So therefore it becomes 4m squared over r squared. If we divide by 1 over 4, it's 1 divided by 1 over 4 becomes 4. So we can check that in our calculator, or we can tip and times it, and we can see that the 4 ends up being at the top. And now that we're at this stage, what this means is that if we factorize this 4 out of the top, because top times top, bottom times bottom, we have 4m squared over r squared. And this initially equaled 1,000. So what we did is we just separated the 4 from the m squared over r squared, because what we need to keep in mind is that in the beginning, 1,000 equaled or represented m squared over r squared. So ignoring this left side, ignoring that for now, what this means is that m squared over r squared represented 1,000. So if we now have 4 multiplied by this representing 1,000, we plug 1,000 into there and we end up with an answer of 4,000 newtons. And this is our final answer. So 1.4, it says a ball is kicked across a floor and it comes to a standstill after t seconds. Cool. So a ball is here. These are little movement lines. Cool. It is rolling until it comes to a standstill after t seconds. So which of the following statements correctly describes the total mechanical energy and the network done on the ball? We have a couple of options. We have not conserved, negative, not conserved, positive, and conserved, positive. So let's break it down part by part. So total mechanical energy, what we're looking at when something is on the floor is our EK before and whether it equals our EK after. Because what is happening, there's no potential energy, there's no height on this ball. It is perfectly on the surface as far as what we've been told. So what that means is that we have half mv squared here, we have half mv squared here. This initial velocity hasn't been given to us, but we do know that it does have a velocity. This is the I. This is the final over there, which means that if this initial velocity is a value, let's just call it 5, for example. M is irrelevant, but let's call this guy 5 squared. There is an actual velocity. Compared to afterwards, they told us it comes to a standstill or rest, which is very important, which means that we have half m and then our v is 0 squared, and anything multiplied by 0 is 0. So over here it has an EK of 0 because it is not moving and there's no potential energy. But at this stage, this guy does have a velocity and therefore there is an EK initially. So let's just call this 25, which means our EK before does not equal our EK afterwards. They are not the same, which means our mechanical energy in this system is not conserved. So B and D are ruled out. So at that stage, we just need to see is the net work done positive or negative? Because net work has to do with our F delta X cos theta. And if there is a ball that is rolling without an applied force, with a normal force going up, a gravitational force going down, the only thing that actually affects the ball that is rolling is the frictional force that opposes the ball, because it is not like someone is pushing this ball constantly, which means the only force actually happening on the object is our frictional force that opposes it until it comes to a standstill. A reminder that net work done is this formula, which means if we have a frictional force over there, our frictional force is negative regardless of the distance. That isn't important. The cos theta here is 180. If ever we have cos 180, it becomes -1, which means it is opposing the direction, which means at this stage we have figured this out because the total mechanical energy is not conserved and the net work done is negative because that is opposing the initial motion of the object and therefore bringing it to a standstill. And therefore our final answer for this guy is A, not conserved, and net work done negative. So then 1.5, it says a crate is given an initial velocity and it slides up a frictionless incline until it comes to a stop. Okay, so we have a crate sliding up a frictionless inclined plane until it comes to a stop. So which of the following graphs shows the correct, so over there, relationship between the kinetic energy, the EK, and the potential energy, EP, of the crate? Okay, so we have A here, this graph is going down with a curve. B here, this graph is going up with a curve. C is going down a straight line. D is going up with a straight line. So what we know in an isolated system when there's no friction, as they mentioned up here, is that our EMEC is our EP plus our EK. Our EMEC does not change though. Our EMEC remains the same, but our EP and our EK change in proportion based on where this block is situated. So let's say our EMEC is 10, but at the bottom our EK will be 10 and our EP will be 0 because there will be movement here at the bottom and no potential energy, because potential energy is based on height. So if this object is on the floor with no height, there will be no potential energy, but there will be the full amount of kinetic energy like a seesaw. So our EK is down here in this situation and our EP is very light, therefore not affecting this seesaw at all. But as we move up and up and up and this object comes to a standstill, it has perpendicular height. It has height there, but no movement, which means the mechanical energy is still the same because there's no friction, but all the energy in the system is given to the system by the EP, as the EP is the only thing carrying the weight, and there's no movement anymore, therefore the EK is 0. And therefore in this scenario, we have a seesaw going down like this. Our EP is contributing to the system entirely and our EK is not contributing to the system, and therefore it still adds up to the total mechanical energy, but just in different forms, with movement at the bottom based on kinetic energy and height at the top for potential energy. So that means these guys are inversely proportional. So D is out of the window, B is also out of the window, but if we move up slightly, this guy might be 8 for the kinetic energy, but 2 for the potential energy, still adding up to 10 for the mechanical energy. And as we move, it starts to shift like the seesaw, going from this position to this position. And at some stage it would be in equilibrium. By that I just mean they would be contributing the same. It will be 5 for the kinetic energy, 5 for the potential energy, but they are moving incrementally and linearly, not exponentially like this guy, which means our final answer here is C, because our kinetic energy here is 10 and our potential energy is 0. As we move a little bit this way, get a little bit more height, we are losing kinetic energy by the same amount. And then this proceeds and continues all the way up until this object comes to a standstill and our potential energy is full, the full 10, and our kinetic energy at that stage is 0. And therefore our final answer here is C. Okay, and then 1.6, it says for light, a red shift indicates the light source moves away from you, towards you, at right angles to you, or D, parallel to you. So 1.6 is just a theory question based on our Doppler understanding. All we need to know is that red means away and blue means towards. This is the end section in our Doppler, and therefore at this stage a red shift indicates the light source moves away from us. This is just something we have to know, and it's just a theory question that we can apply and move on. So that is our final answer, 1.7. So 2 point charges of +7 nanocoulombs and -5 nanocoulombs are brought together until they touch. Immediately after that, they return to their original positions. So which field pattern correctly represents the charges when they are back in their original positions? Okay, so we have 2 guys repelling, so like charges, but the arrows are going towards. 2 guys also same thing, but the arrows are going away. 2 guys that that are attracted to each other, and then these two guys where we can see the field lines are crossing and different length and quite irregular looking. So at this stage, what we need to do is work with this first information, going Q new equals Q1 plus Q2 divided by 2. I'm going to leave out the nanocoulombs in this situation as we don't need to apply it in here. What we're trying to look at is not the amount or the degree in terms of nanocoulombs or microcoulombs or what have you, but just seeing whether they are repelling or attracting one another. And then from there, seeing whether they are positive or negative ultimately as to which direction the arrows will be going. So if we have positive 7 plus minus 5, we are there, divided by 2. 7 minus 5 is 2. 2 divided by 2 is positive 1. Then I'm just plugging in the nanocoulombs now, which means they are both the same charge, as we would know from this formula, but they are both positive, which is very important, which means they will be repelling, which means it isn't D, it's not this irregular one. They also are not attracting one another. The only other thing to keep in mind is that E equals F over Q, not because of the application of the electric field, but because this formula helps us remember that it is per unit positive charge. So attraction moves from positive to negative. So what we're doing, if there's a positive speck of dust in this environment, it'll move from there to the negative. That is just a nice framing or way to remember that arrows are going away from the positive, which means these arrows here will be going here, which means these will be negative, and this does not fit what we want. A is therefore out of the window, but a positive 1 means our answer is B, as it moves away from the positive to the negative. And both of these are positive 1, exactly the same, and positive meaning they are moving away from these guys to whatever negative charges are around them. Cool. And B is our final answer over there. 1.8 over here. A non-ohmic resistor can be described as a resistor for which. So if A, Ohm's law is valid, B, the current potential difference graph produces a straight line, C, the resistance does not vary with the change in temperature, D, the resistance is not constant and varies with the applied potential difference. So off the bat, non-ohmic resistor. Ohm's law, as we know it, V equals IR, is that the potential difference in a conductor is directly proportional to the current across a conductor when temperature remains constant, which means that if we have a straight graph, say now this is our V, that is our I over there, it will give a straight line, because what we're saying is as we increase the amount of batteries in the circuit, the rate of flow of charge will increase as well, provided the resistance stays the same. The reason we say that when temperature is constant, as when temperature increases, it affects the amount of resistance we have. So what this means is that if we keep the temperature constant in a perfect condition with an ohmic resistor, it means the voltage will go up, the current will go up, it will be a straight line. So off the bat, a non-ohmic resistor does not obey Ohm's law, because Ohm's law tells us that the temperature is constant, but a non-ohmic resistor is a light bulb, for example. So as the current flows through a light bulb, the light bulb will increase in temperature, as we know, and therefore the resistance will change and the proportion of the voltage and the current will change as well. So Ohm's law is not valid for a non-ohmic light bulb. The current potential difference graph produces a straight line. That is also not true for a non-ohmic resistor. As we mentioned, the temperature will change and therefore it might taper off like that, because the voltage can increase, but because the temperature has gone up, therefore the current will not increase in proportion. So therefore B is out of the window. C then, the resistance does not vary with a change in temperature. That is also not true, because as it gets hotter and hotter, the resistance gets more and more. So therefore the resistance does not vary with a change in temperature. This is also not true for a non-ohmic resistor, which means we have eliminated the first three, which means D, the resistance is not constant. That is true, as we can see here, because this graph over here tells us resistance. If we take the gradient formula, R equals V over I there, which means the resistance is the gradient here. If we would do change in Y over change in X, okay, that just means I would have to swap the X and the Y, put the current on the bottom here and the voltage here, because if we do change in Y over change in X, we have V over I, and that gives us our resistance, which means our resistance is the gradient of this graph. But now we know that the resistance is not constant and varies with the applied potential difference, which is true as well, because as we increase the potential difference, it increases the heat, and therefore the light bulb increases in temperature, which changes the resistance. So therefore our final answer here is D, earning us 2 marks over there. Cool. And then 1.9 over here, there was an error on the memo, as they said the answer was C, but we're still going to break down the section and the thinking and theory used behind it. But it says 4 identical resistors are connected as shown below, which connection will result in a total resistance of 4 ohms. So we have a couple of formulas here. We have our resistance in series, R1 plus R2 plus however many resistors in series there are. And then our resistance in parallel, 1 over RP equals 1 over R1 plus 1 over R2, etc. Okay, so we're just working with different combinations of resistors in different arrangements, and we're trying to see which one adds up to 4 ohms. Let's just call this guy 1 and ignore the fact that they are identical. As mentioned, the answer should be C according to the memo, but C in this arrangement does not give us 4. It gives us 5, just like this arrangement B, because 2 plus 2 is 4, and then when we work out this parallel branch, it adds up to 1. So 2 plus 1 adds up to 5, and that would be the same here before we turn this into a 1, where 2 plus 2 is 4, and then this adds up to 1 as well, which adds up to 5. So we're just trying to get the answer in this case, but what we're doing here is we're working out the different sections. So we've already done the series here and the parallel here, because 1 over 2 plus 1 over 2 adds up to 2 over 2, which equals 1. And if we were to flip the 1, as we have to do because we have 1 over RP, or we go 1 to the negative 1, which some of my students prefer, then we still have 1 in this case. So then we had 2 plus 2 is 4 plus 1, and we have 5. So 5 ohms is out. So we're going to go to C last. We're just going to practice working through each of these. A, we have 2 plus 2. So there's a 4 on this parallel branch, because we can just add up these 2 resistors in series and act as if there were 1 resistor on this parallel branch. So we have 4 ohms over there, and we have 4 ohms over there, which means we have 1 over 4 plus 1 over 4 over there, which means we have 2 over 4, and then this is to the power of negative 1, which means we have 4 over 2, and this adds up to 2 ohms over there. So we have 2 ohms over here, this guy's out, we have 5 ohms over there, that guy's out. Then we're going to work with D before we see that C gives us our answer with the change that we made. Then we have 1 over 2 plus 1 over 2 plus 1 over 2, and that adds up to 3 over 2 to the negative 1. As a reminder, this all equals 1 over RP, so we do have to flip it at the end. Then at this stage, we have 2 over 3 for the parallel section over here, which is 0.67 plus 2, which is this resistor in series, which means we have 2.67 ohms over there. So that means we only have one option left, which is C in this situation, and therefore 1 over 2 plus 1 over 2 equals 2 over 2, which equals 1 to the negative 1, which equals 1. So we have 1 plus 1 is 2, 2 plus 2 is 4, and therefore we have 4 ohms over here, and our answer is C. But once again, the memo was wrong here. We had to change this question to make it work based on the memo, removing the identical resistor to get the total resistance of 4 ohms. Cool. And then final question for this section, 1.10, a kilowatt hour refers to A, the use of electrical appliances. Okay, it's not that. B, the power of electrical appliances. Also not that. C, 1 kilowatt of electricity used for 1 hour. It is that. A and B were not close to that. There are applications of it in the electricity section, but they are not the answer because we use it for electrical appliances, and power is represented in watts, or if we do a conversion, kilowatts, but not the hour portion. So it is C. And then D says the cost of electricity specifications. That is also not true, but we do use kilowatt hours when we multiply it by rands to help us calculate the cost when we are in the electricity section. So this is also just a theory question, and we just need to understand that it is C over here, and that is our final 2 marks for this section. Cool, guys. So this is question 2 of the physics paper. This is the beginning of Newton's, and let's jump right in. So we have a person pulls a block of mass 12 kilograms over there to the right using a light inextensible rope T. So we have tension. The block is pulled from point A to point B over here at an angle of 40 degrees between the rope and the horizontal surface. The coefficient of kinetic friction between the block and the surface is 0.31. That is good for us. The block is pulled at a constant velocity. Okay, they are shouting at us. That is important to note, which means there is no acceleration in this system. Okay, of 10 meters per second to the negative 1 as shown in the diagram below. So here is the guy, here is the block, there's the mass, we are good to go. So 2.1, we are jumping into a definition, which usually leads us to use that definition in some sort of formula later on. So just saying, define the term kinetic frictional force. This is an all or nothing question. By that it means we either get 2 marks or we get none. I saw that in the last set of exams, this cost a lot of my students a lot of marks, considering this is about 15% throughout the whole paper, all the definitions, and if you get none of them, then you lose about 15%. 1%. Same with the multiple choice, it actually adds up to quite a lot. So just getting the definitions down and getting the multiple choice right can automatically raise your mark by about 20%. So that is important to note. Cool. So off the bat, the kinetic frictional force is the force that opposes the motion of a moving object relative to a surface. So this is all or nothing question, but it does help us orient ourselves as to using this formula later on, which means if they ask this definition, they are most likely going to use this kinetic friction formula somewhere later on. So off the bat, we just earned 2 marks over there. So 2.2, it says draw a labeled free body diagram of all the forces acting on the 12 kg block while it is moving at a constant velocity. Okay, so this is also a good question as it helps set up everything we need to see which forces we need to work with as we move into the formulas coming up. So we always have gravity acting down, so we have Fg. We always have Fn going up there. We have frictional force here because they gave us the coefficient of friction, so there is kinetic friction working against it. Doesn't matter the lengths of each side, they don't have to be drawn to scale, but the direction is important. And we have tension going up here, and that'll be our 4 marks. Sometimes they will say for a 5th mark, give 1 angle, and then we draw a dotted line over here, and we would have our 40 degrees over there. One thing to keep in mind though is that we don't do the components of something at an angle, something like tension. I'm going to draw it now, but we don't do the f of y going up there and the f of x going down. But we do use those in our formulas going forward, which means we just need to draw another free body diagram to help us remember that we must use the components as we move into the formulas. So that is 4 marks right there, not including the dotted lines for the components of tension. Cool. And 2.3 now. So it says calculate the magnitude of the tension in the rope. So one thing to keep in mind, if we're trying to calculate the tension in the rope and the magnitude for 5 marks, it means we are probably going to work with one of these components. At this stage, this block isn't moving up and down as gravity and the f of y plus the f of n are in equilibrium. This block isn't lifting off the surface, it isn't sinking into the ground either, which means this direction, this up and down direction, isn't what we're working with. But we are trying to work in this horizontal plane where we can do a perfect math sum of plus a direction minus the other direction, because we always have to work either completely horizontal or completely vertical to do some type of sum. We can't go t here at this angle minus f of f here because we don't have a perfect linear direction, a perfect horizontal. Cool. So that is just something to keep in mind as we plug into this formula. Cool. So at this stage, we are working with some type of F net formula. We just need to see, are we working with Newton's 1 or Newton's 2? Because they have shouted at us, they have put in capital letters that it is a constant velocity, which means there is no acceleration. 10 meters per second to the negative 1 is our velocity, but it is constant, which means there is no acceleration, which means our mass times acceleration is 0, because 12 times 0 is 0, which means we just have to work with the F net for our horizontal plane on this side as we unpackage it. So F net over here, if we have a positive direction, as it is moving in the direction that the person is pulling it in, it is moving in the direction of f of x. This will be our positive, and our frictional force will be opposing it, and it will be negative that way. So it helps to pick a positive and a negative so that when we unpackage our F net, our resultant force, we can then include the signs that are in line with the direction that the object is moving in, which means here we have our f of x minus our frictional force, and that is everything on the left side. These are the only two forces working in the horizontal plane. So one thing to keep in mind when we are pulling any object at an angle, here's our tension, we have our t of y over there, and we have our t of x over here. We need to determine which one is cos and which one is sine. We can always use normal trig to do that, but a nice way that I like to remember it is that our y component is just sine with a y plugged in there, which means our x over here, I just write it like this, but if we understand that sine has a y in there, we'll know that our y component is by sine, and therefore our cos has to do with our x value. So that means if we are working with the x value, the horizontal component, we are working with cos of the angle that they've given us. So off the bat, for our f of x, which is our tension, we just have t cos 40. We want tension, but we don't have to unpackage it. We can just add the cos 40 because we are working in the horizontal plane. But what is important is unpackaging our ff. A reminder that we used the kinetic frictional force, or that was the definition we had to define in the beginning, which means we are using that formula over here in our calculation, which means we have u times fn, and that is our ff component over here. And this still equals 0 because there is a constant velocity and therefore no acceleration. So we can just go ahead and start to solve it by plugging in the variables for our frictional force. So T cos 40 over here minus our coefficient, which is 0,31 as they gave us earlier. So we have 0,31, and then we just need to calculate the normal force, because the normal force is the gravitational force equaling the normal force plus the tension of y, which means if we are trying to isolate our Fn, let's just write this first. So Fg equals Fn plus Ty, which means at this stage Fg we can calculate, but let's just isolate for Fn. So in order to isolate for Fn, because these guys are in equilibrium, this box is not falling through the ground or lifting up off the surface, it means these are in equilibrium. This equals this plus this. But now what we want in this formula here is our F of n, which means we're going to take our Ty over, and therefore our Fg minus our Ty equals our Fn. So this is what we're going to plug into this formula here, this big placeholder here, but we can calculate some components of it, because Fg is our m times g, which is our mass times gravity, 9.8, and we have the mass of the object. So what we're going to do, we're going to go 12 times by 9.8. Over there is our Fg minus T of y. A reminder back to this graph over here that our tension of y, we still don't know tension. Tension is unknown. That is what we're trying to calculate. But the y component, if x was cos, our y is sine of that same angle based off of our horizontal. So this 40 over here, which means we have T sine 40. And this whole thing, once we've simplified the Fg just to a number, is what Fn represents. So we can then go ahead and plug that into there. So 12 times 9.8 is 117.6 minus T sine 40. So that means we can just go ahead and we can plug that into our formula here where our Fn is. That means we have 117.6 minus T sine 40. And this still equals 0. At this stage, we can just go ahead and we can solve for everything. Even though this T cos 40 and this T sine 40 might look daunting, cos 40 and sine 40 are just number values, just like special angles in math, which means we can just go ahead and we can start to solve for everything. So what we're going to do is we're going to turn our cos 40 and our sine 40 into number values. We're then going to distribute our 0,31 into both of these guys, and then we're going to take the numbers to one side, simplify our T with the numbers, and then we can divide by it to get an actual value for tension in this equation. So cos 40 equals 0,766 T, never round off until the end. So that's why I'm just putting the dots here, minus sine 40 is 0,64278 T. 117.6 was here, and then we still have our 0,31 to distribute into both of these. Okay, so then at this stage, I'm going to distribute the 0,31 to both of them, and this equals 0,31 multiplied by 117.6 equals 36,456. And that was there, negative 0,31 multiplied by 117.6, and then negative 0,31 multiplied by negative 0,64278 equals positive 0,1992 T. And that is this guy distributed to this whole thing over there. And this all equals 0. So at this stage, we can just take the number over to that side, simplify our like terms with the T on them, and then we can go ahead, divide by that, and we'll have our final answer. So taking this over, we have positive 36,456, and then simplifying the 0,766 plus the 0,1992 together equals 0,9653 T. And then we can just go ahead and we can divide by this 0,96 and the 0,96 over here. And our final answer over there for tension is 37,77 newtons. And that is our final answer for tension. So we just earned 5 marks there, and we have the tension in the rope over here. So then 2.4, the block is moved a horizontal distance from A to B of 24 meters. So 2.4.1, calculate the time it will take the block to reach B. Okay, so there are bridging equations of motion and the force section. That's why we have both of them up here. So we have a bunch of variables. Cool. So let's write them down. That's always a good practice. We have our VI, our VF, we have our delta X, we have our A, and we want time. So at this stage, what we we need to look at. Our initial velocity is 10 because they said it is starting at 10, but it is a constant velocity from there to there. They did not use the word rest anywhere. So our final velocity is also 10. Our distance is 24, as we just read over here, 24 meters from A to B. Our acceleration, because it is a constant velocity, is 0. And time is what we want, which means we need to try and calculate time, which means we need to go to a formula that has time. So we have our formulas with time over here. We have this guy, but this won't work to give us time in this scenario because our acceleration is 0. So 0 multiplied by anything means that is 0, and then our time will disappear. So we cannot use this option. This option over here does not have time in it, so that guy's out of the window, which means we're dealing with either of these two, where we have a distance and a time, or a distance and a time. So I'm going to go ahead and write our delta x equals vi times delta t plus half a delta t squared, and then we can go ahead and we can solve that, or we can use this formula as there's no change in acceleration, which means over here we have delta x equals vi delta t plus half a delta t squared, and then our delta x over here is 24, our vi is 10, delta t is what we want, plus half a is 0, so this whole portion of the sum is just going to disappear. Delta t over here is what we want, but that is all going to go, which means we have 24, and ultimately this just becomes speed equals distance over time. And then we have that, delta t is there, and then we can just go ahead and divide 24 by 10 to get delta t, which means we have 2.4 seconds. And that is our final answer here, accounting for the fact that there's no acceleration and earning us 3 marks over there. So 2.4.2 now, it says if the block's velocity is increased to a constant velocity, so no acceleration still, of 20 meters per second to the -1, how will the frictional force be affected? The frictional force, right, only increases, decreases, or remains the same. So with these sort of questions, it's very good to go to the formula. Once again, this definition was referring to this question as well, which means that if we rewrite our formula for frictional force, we have Ff equals UFN, or our mu over here, which means our frictional force will only change if we change the coefficient of friction, if we increase it. And the only way we can change the coefficient is by changing the texture or the type of material that the surface is made of. So ice will have a very low coefficient because it is quite slippery, but sandpaper will have quite a high coefficient because there's a lot of friction based on the type of material of the surface. And over here, we also have not increased the Fn, we have not increased the mass of the object or the angle at which we are pulling the object, considering there's an Fy over here that affects our Fn based on our previous question. So if we are not changing the coefficient or the normal force through means of mass or the angle at which we're applying a force on the object, it means that the block's velocity increasing without any change in acceleration will not affect the frictional force, and therefore the frictional force will remain the same over here. And that just earned us 1 mark. Always write it out exactly how they write it so that you can guarantee that you get the marks. And then 2.5, almost done with this section. The angle between the rope and the horizontal surface is increased to 50. Okay, so this guy is now pulling it at an angle like that, for example. There's a 50 from the horizontal up to the new angle that the rope is being pulled from. So what will be the effect on the kinetic frictional force acting on the block now? Okay, so 2.4.2 leads into 2.5, including an aspect of what we were talking about here. So the effect on the kinetic frictional force acting on the block. So let's see what happens. So a reminder that we had Fg going down, we had Fn going up, and we also had our Fy going up. But in this scenario, our Fy is increasing because our angle is increasing. 2.5.2, we're about to explain our whole answer, so we'll write that there. But at this stage, Fy was pretty strong previously, but as we increase the angle, our Fy becomes stronger and our Fx becomes less. So at this stage, if we are plugging an Fn into our Ff formula, Fg equals Fn plus Fy, okay? But a reminder that we increase the angle, our Fy is increasing. So when we take our Fy over, our mass of the object has not changed, but our Fy is a bigger value now because we have increased the angle. So that stays the same. I'm just gonna put an equals sign over here for our Fg. It is the same, but our Fy has increased, which means we are minusing by a bigger value, and all of this represents our Fn, which means our Fn here is going to become becomes smaller, because what is happening is this object is lifting slightly off the ground, not entirely, not in any visible way, but it is lifting a little bit more off the ground, which means our Fn can work less hard because our Fg and our Fn plus Fy are in equilibrium. So our Fg is the same, but because the Fy is increasing, our Fn can work less hard, as if there are people on a tug of war team and therefore have to equal each other. So because Fy is increasing, Fn can decrease, and this team on tug of war can still pull the same as the Fg over there. So that means our Fn is decreasing. Our coefficient has not changed. The material that the surface is made of has not changed, but our Fn is going down. So if our Fn is going down because we increase the angle, the kinetic frictional force acting on the block will also go down because it is directly proportional to the Fn. So if Fn goes down, our frictional force goes down, and therefore our answer is decreases. And that'll earn us 1 mark over there, and that was the explanation for 2.5.2, which we'll just revise now, but explain the answer of question 2.5.1 for 3 marks, which means 3 bullet points. So our angle to the horizontal has increased, therefore our Fn has decreased, and therefore our Ff has decreased, as it is directly proportional to Fn. And that explanation will earn us our 3 marks. Our angle has increased, therefore our f of y has increased, our Fn then decreases, and therefore our Ff decreases as well, because our Fn is directly proportional to our frictional force. Cool. And that is 3 marks for that last question of this section, earning us 19 marks for this whole section. Cool, guys. So we're checking out question 3, Newton's law of universal gravitation. It says a rocket of total mass m is launched from the surface of the Earth. The initial weight of the rocket is 5.38 times 10 to the 6 newtons. That is important. The mass of the rocket decreases due to the loss of fuel that is used to propel the rocket. When the distance between the center of the rocket and the surface of the Earth is 9,000 meters, that is also good for us. Meters is important because this formula is measured in meters. So the rocket experiences a gravitational force of 5.04 times 10 to the 6 newtons. So we have this guy over here. So that is our gravitational force. That is our F for this one. And this is the weight in newtons. So we'll have to get the mass to unpackage it to put it into there. Okay, the diagram below is not drawn to scale. So we have Earth, we have the rocket, we have the radius, the distance from this center to the center of the Earth, and the moon over here. So 3.1 for 2 marks. It says state Newton's law of universal gravitation in words. Okay, so this one's quite nice. It is this formula up here with just a couple of words beforehand. So each body in the universe attracts every other body with a force. Cool. So now we are jumping into this formula. A force that is directly proportional to the product of the masses and inversely proportional to the distance between their centers squared. That is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Great. And that will earn us 2 marks. The important phrases are their centers and masses. So with that, it is telling us that we are going to use this formula going forward, but a law always needs to be verbatim, needs to be said exactly how it is in your definition breakdown. And then from there, 3.2, it says calculate the 3.2.1 total mass m of the rocket before it launched. So the initial weight of the rocket is 5.38 times 10 to the 6 newtons, which means the mass has to do with this. Before it launched means that it was on Earth as well. So that is pretty good for us, which means we can just go ahead and use our W equals mg or our Fg equals mg, which means its weight was 5.38 times 10 to the 6. Its mass is what we want, and gravity on Earth is 9.8. So we can just go ahead and we can divide this 5.38 times 10 to the 6 by 9.8, and we will have our mass. And our mass is 548,979,59 kilograms. So we just earned another 2 marks over there. And with that, this is a follow-on question. So we are most likely going to use 3.2.1's answer in 3.2.2. It says the mass of the rocket when it is 9,000 meters from the surface of the Earth. Okay, so that is not including the center of the Earth. Okay, the fact that they said surface of the Earth means we have to take into account the radius of the Earth as well, because our Newton's law of universal gravitation tells us that it is between their centers. So we just need to account for that whenever we see the word surface. But this means 5 marks. We're just trying to plug in all the different variables into this formula up there. So I'm going to write this formula down so long. So we can go ahead and start plugging in the different variables. A reminder that this F here is the gravitational force. This G is the gravitational constant that is up on our formula sheet. Mass 1 and mass 2 are the masses of the objects that we are referring to, which is the Earth in this case, and the rocket, which we just calculated in the previous question. And the radius is the distance between their centers. So the force over here, we were given it in our writing. So it is 5,04 times 10 to the 6. The gravitational constant is up here, which means we have 6,67 times 10 to the negative 11. The mass of the rocket is what we want. So that is one of our masses. And then the mass of the Earth is what we want to fill in here. And that is given to us all the way up here as one of our constants. So we have 5,98 times 10 to the 24. And then we have our radius. So it is 9,000 meters above the surface of the Earth. So we're going to write that down. The fact that it is in meters is very good for us because we want it in meters. So 9,000 is there. And then we also need from the surface of the Earth to the center of the Earth. And that is also given to us as one of our constants, as we mentioned, which means we have to add this. It is also given in meters. So this is helping us see that it is always given in meters, the radius. So we have 6,38 times 10 to the 6 as well. So we are going to add them together. And then at this stage, we have added them together, and just don't forget the square over there. At this stage, we have plugged in all the variables and all the information in order to calculate the mass of the rocket over there. So all we need to do is solve for them. So in my calculator, I'm going to put everything on this side, excluding the m, so I can just simplify all of the numbers here. So 6,67 times 10 to the negative 11 multiplied by 5,98 times 10 to the 24 divided by this whole bottom portion. Once we have simplified that, we'll have that multiplied by m, and then we can divide that on this side, and then we can isolate for m. So I'm going to go ahead and plug this into my calculator, the right side excluding the m, and on the right side we have 9,771500 m. So we have simplified all of this in our calculator, and this still equals 5,04 times 10 to the 6. So at this stage we can just divide this underneath here. So we're going to go 5,04 times 10 to the 6 divided by 9,77, and that equals m, and then we'll have the final answer of the mass of the rocket when it is 9,000 meters from the surface of the Earth. And our final answer is 515,785,70 kilograms. Great. And that just earned us 5 marks over there. And now 3.2.3, it says the mass of the fuel that was consumed when the rocket reached 9,000 meters from the surface of the Earth. So this is also a follow-on question using 3.2.1's answer and 3.2.2's answer. So we just need to subtract them from each other, and we'll have our final answer there. Because in 3.2.1, the total mass of the rocket before it launched was this over here. So we can bring it down. So we have 548,979,59 as its initial, but then as it travels, it loses mass because of the loss of fuel, as it mentioned up here. And then over here, we calculate the mass of the rocket when it was 9,000 meters. And as we can see, it was a little bit less. So what we're trying to do is calculate the difference between the two, so we can figure out how much fuel we used. So I'm going to subtract this value here, and then we can just go ahead and subtract these two in our calculator. And the final answer for the mass of the fuel that was consumed when it reached 9,000 meters is 33,193,89 kilograms. And that just earned us 2 marks over there. There's no formula or no marks for any formula here. It is just helping the understanding that this was the total mass of the object, including the fuel, and this was the mass of the object after it has used up some of the fuel because it had traveled a journey of 9,000 meters above the surface. And then 3.3, the final question here for 2 marks. It says the rocket is on its way straight to the moon. What will happen to the gravitational force between the moon and the rocket as the distance between the Earth and the rocket increases? So what will happen to the gravitational force between the moon and the rocket as the distance between the Earth and the rocket increases? So we have to write only increases, decreases, or remains the same for 2 marks. marks. So our answer is increases, and that is because the further it moves away from Earth, the less gravitational force the Earth applies on the rocket, due to the fact that the radius is bigger. We are dividing by a bigger number, therefore the force is smaller. According to our law, they are inversely proportional, because this is just a way that they phrase the question, because as it moves further away from Earth, it is moving closer to the moon, which means they're asking the gravitational force between the moon and the rocket, and the gravitational force between the moon and the rocket will increase as the radius gets smaller, which means we are dividing by a smaller value here, meaning there'll be a bigger force of gravitation between the moon and the rocket. And that is our final answer there for 2 marks, earning us 13 marks for this whole section. Hey grade 12s, so if free fall is starting to get a bit confusing, we're going to break down the question 4. We're going to show the whole structure and approach to this question, as well as the usual formatting that they ask in all of the exams, so that you can feel more comfortable when you approach this question by yourself. Cool. So let's jump right in. So question 4 says a hot air balloon moves upwards at a constant velocity. That is important. When a block B is dropped from the side of the balloon and falls to the ground. The balloon is 50 meters above the ground when the object is dropped initially. The graphs below show the motion of both the balloon and block B. The graphs are not drawn to scale. Ignore all effects of air resistance. Use upwards as positive in all calculations. Very important. So what we have here is a velocity time graph for balloon and block B. As they mentioned, we have our velocity on the left, our time on the x-axis over here, and our positive direction is the initial direction. So everything above the line is positive, and the initial direction that the block and the hot air balloon are moving in. So 4.1, it says which one, the balloon or block B, is in free fall. So they love this. They usually start this question either with a free fall or a projectile sort of definition or interpretation type question. So it says give a reason for the answer. So off the bat, the thing that is in free fall meaning that only gravity is acting on it, is the block over here. So our block B is in free fall. And once again, the reason is just a definition. This is just a different way of saying give the definition as to why it is in free fall. So therefore, only gravitational force acting on it. Cool. And that would earn us 2 marks. So the reason this is true is because of inertia. So even though the block was dropped, it continues with the same initial velocity as the balloon before it slows down to 0 and then changes direction. A reminder that whenever we approach 0 in a velocity time graph, it means we are changing direction. So what is actually happening is that this balloon is continuing up like that, okay? But this block over here is continuing, but it was dropped, so slowing down until it reaches 0, and then it changes direction. So the 0 point where it stops is over here. It was initially at 5, but it is slowing down in terms of velocity, as we can see here, as it bends to 0. And then as soon as it reaches its peak height and the 0 velocity, it starts to accelerate downwards. And that is what's happening here. This whole motion is it accelerating downwards until it hits the ground. So this will help us with our sketch over there for the position time graph, but it is very important to note how to interpret the velocity time graph, and that 0 is our reference point where it starts to change direction. So 2 things: they love the hot air balloon scenario because of the initial velocity of the block being the same as the initial velocity of the hot air balloon, even though it is in free fall. So right now we've answered 4.1. We understand a bit more what is happening in this question. And then 4.2 says using only equations of motion, calculate the following values. Okay, so we have our equations of motion up here, and it says 4.2.1, the time t1 over there. Okay, so t1, if we zoom in, is the point when it reaches 0 here. So it means it has an initial velocity and its final velocity will be 0. So this is always important to write down what variables we have. If we want time, that is going to be our question mark. Then our VI in this case is 5 meters per second there. Our VF at time t when it reaches 0 is 0. Our distance, we don't know. We don't know how far it traveled up from the 50 meter mark, because a reminder that from there to there is 50 meters. They told us that over here, but we don't know how much higher it traveled upwards. So we don't know the distance it traveled to that point, but we might not need to. And then in this scenario, we always have acceleration, and acceleration is minus 9.8. The reason that it is negative and the reason that it is important that we keep it negative is because they told us upwards is positive in all calculations, and gravity is acting downwards downwards towards the Earth. So we always need a positive and negative direction, and that helps us interpret this section a lot more clearly. So we have an A, we have a VI, we have a VF, we want T. It is only 3 marks, so this first equation here will work very nicely for us. So we can just plug in our values and solve for T there. So I'm just going to write this down, and then we can start substituting all of these values in. So our final velocity is 0. Our initial velocity is positive 5 as it is going upwards. Our A, as we mentioned, is negative 9.8, and our time is what we want. So we can take our 5 over, so it becomes negative 5. Then we have minus 9.8 delta T, and then we can just go ahead and divide by negative 9.8. So negative 5 divided by negative 9.8, and our time is 0.51 seconds, and it is a positive value as time is a scalar. So if we divided our 9.8 and we had a negative time value, it means that we didn't substitute a negative in correctly. So if we plugged in 9.8 but we didn't make it negative and we had a negative time, it means we must just go back and check our work because we didn't put in the correct negative based on which direction is positive and which direction is negative. So we have the time for T1 over there, earning us 3 marks. And then 4.2.2, the velocity V of block B. So the velocity V is over here. It is the final velocity when the ball hits the ground. Okay, so it was 50 meters above the ground, and it says it falls to the ground. So V over here is the final velocity when the ball hits the ground. So the question following that is T2, and that is the time that it hits the ground, but we'll get there. So the velocity V of block B. So what we can do, and what we started with, is the time it took for it to go up. So one other thing we can keep in mind, and that is important for the section, is that the initial velocity the block went up with was 5 meters per second, but it was positive 5 meters per second. But then as soon as it comes down and it is perfectly in line with where it started, it will be negative 5 meters per second. So what we can keep in mind is that the velocity here and here is exactly the same in terms of numbers, exactly the same magnitude, but it is just a different direction, and therefore one is positive and the other is negative. So that is very important to keep in mind, which means we can always split up this whole distance into segments as far as it going up and then it going down, and then from here it going down if we want to. But at this stage, what is important for this question, if we just want the velocity V of block B, we want this VF over here because that is a question mark. It means our VI, we can just take it as the VI here with a positive 5 meters per second to the negative 1. We don't have to take the whole journey here, all the way to here, all the way to there. We don't have to segment it if we prefer not to. That means at this stage, we're using a different formula. We're using VF squared equals VI squared plus 2A delta Y. We're about to see why and how this works. So our final velocity is what we want. Our VI in this case is 5 meters per second squared. So it is a positive 5 meters per second. So we have that multiplied by 2 because that is a part of our formula, multiplied by negative 9.8 over there. And then our delta Y, what is important is that we don't have to add up how far the distance was over here. We can if we prefer that method, but what we are doing is plugging in 50 meters from here to here. The fact that this is positive and this final answer will be negative means that the positive and the negative are accounting for the 50-meter journey from here to here, not including from here to the top and from the top back in line with it, considering they have the same velocity here and here. So we can just plug in the 50 there. If we don't prefer this method, then we can always segment it, figure out the distance from here to here, and then just track this whole journey from however high it is here until it hits its final velocity there. That is also good. But let me know if there are any questions in the comments as far as clarifying this, and I will show the other approach in another video. So at this stage, delta Y is 50 meters, and it is displacement, so we have to make it a negative 50 because everything here is a vector except for time. Acceleration is a vector, so therefore it has a direction. So does the initial and final velocity, as well as the delta x, delta y, our displacement. So the fact that it is going down in a negative direction means we have to have a negative 50 there as well. So at this stage, we have numbers on the side. We can just simplify them in our calculator, take the square root, and account for the fact that our VF is going down, which means it won't be negative because of the square values we have here, but we do have to say that it is whatever magnitude we've calculated downwards. So at this stage, we can just plug this into our calculator and then we can go ahead and solve for it. So we have 1005 over there, big number, but this represents VF squared, which means we can just go ahead and square root this, and our final answer is 31,70 meters per second to the -1 down. Cool. And that just earned us 3 marks over there, and now we have the final velocity with which the block hits the ground. And then at this stage, for 4.2.3, they want the time t2, the time when the block hits the ground. Okay, this is also 3 marks, and we have an initial velocity, a final velocity, an acceleration, and we want time again, which means we can go ahead and use the first formula over there. So we're using the first formula over there, but we can use any other formula with time in it. Ideally, this delta y vi delta t plus half a delta t squared. That is also an option, but either way, both of those formulas will give us an answer that is within the range on the memo, considering there are lots of different ways to get to the same final answer. So time t2, I'm just going to go ahead and write down the formula that we're going to use together. So that means our VF is over here. It's our 31,70 down, which means it has to be negative based on the fact that down is negative. So we have that over there. Our VI still we can take as positive 5 meters per second, considering we are using the initial velocity that it had. Our A is negative 9.8, considering gravity is pulling it downwards. Cool. And then time is once again what we want over here. So at this stage, these two guys are multiplying, so we're going to deal with them last. So we can take 5 over and make it a -5. So we have negative 36.70 equals minus 9.8 delta t. So then we can go ahead, divide by negative 9.8 on both sides, and our final answer for delta t over here is 3,74 seconds. Okay, and that just earned us another 3 marks over there. And then we're on question 4.3, the last question of this section, for 5 marks, and they usually structure the questions like this with some sort of sketch at the end. So it says sketch a position time graph, very similar to what we did over here, almost identical, even though this just helped us with the explanation. Sketch a position time graph of block B from the moment it is dropped until it reaches the ground. Use the ground as 0 reference point. That's always important. Clearly indicate the following values on the graph: the initial height, the time at maximum height, the time when block B reaches the ground. They always give these bullet points here, and these bullet points here are always the exact same things that we worked out here. We never have to calculate anything further when we do a sketch. It is always the values that we calculated previously, and then we just plot it accordingly. If we don't have the values to plot this graph, it means we might have made a mistake up here, or if we need to calculate something further, we just need to double check that we don't already have what they're asking for. So we just need to make sure that these values over here, the things we calculated, are in fact the things we are plotting on the graph. So we can just go ahead and draw our position time graph. I'll draw the axes and the labels along. Okay, so we have our position versus time graph. We have position in meters on our y-axis and our time on the x-axis in seconds. We don't need a scale or anything. What we need for this is a general shape, just like this graph that they've initially given us with a general shape. Velocity time graphs, they are usually sharp and jagged, and then our position time graph looks like this, imagining you throwing a rock off of a cliff. It'll follow the same trajectory that you see. So that means we're just going to go ahead and draw this. The reason that the block doesn't just go like this, as we discussed, is that there is an initial velocity due to inertia. So it continues in the same direction until it slows down to the 0, and then it changes direction and accelerates downwards to the ground, ultimately hitting the ground. So it is exactly the same as what we had over there, just as if it was thrown off. But it wasn't thrown off, it was just under the influence of inertia, continuing in the direction of the balloon before it started to change direction. So what they want here, we've drawn the axes, we've sketched the general shape, that's great. And now we need the initial height. So we can just approach this like a checklist. The initial height we had here was 50 meters before it started to journey up. So 50 meters we have over there. That means we didn't have to calculate how high it went up, nor do we have to plot that distance up until the peak. So the initial height, we have that there. The time at maximum height. So that is the time t1 when it reached 0 all the way up here. And we had the time here from our previous question. It was 0.51 seconds. So we can just go ahead. Let's say that is our peak over here. Plot 0.51 5.1 over there. And then last bullet point they want from us is the time when block B reaches the ground. So the time for the total journey, we had that over here. It is 3.74 seconds, and that is when it hits the 0 reference point, 0 being over here. So then we can just plug 3.74 there, and that would earn us our 5 marks for this question and 16 marks for this whole section. Cool. So if momentum is getting a bit tricky at this stage, we're about to break down question 5. We're going to see the whole structure of a question like this, see the application of momentum, as well as some vector diagrams and change in momentum, i.e. impulse. So let's jump right in. So question 5 says the vector diagrams below show the momentums of car A, mass 2,000 kilograms, which is traveling to the right, before and after a head-on collision with stationary car B. Cool. Then it says the collision lasted 0.5 seconds. Okay. After the collision, car B moves to the right with a speed of 20 meters per second to the -1 to the right. Okay. So the diagrams below are not drawn to scale. Vector diagram for car A before and after the collision. So we have an initial momentum of 30,000 kilograms per meters per second to the right. And then we have a final momentum of 10,000 kilograms per meters per second to the right. Okay. At this stage, before we start to break down the application of these questions, we're jumping into a theory question. 5.1 says, state the principle of conservation of linear momentum in words for 2 marks. So this one is quite a nice one. So what we have is the total linear momentum of an isolated system remains constant. So this just earned us 2 marks over there. The total linear momentum of an isolated system. Okay, so it means that no momentum is lost in the system. It is only transferred from one to another, meaning that there is no friction or anything like that, air resistance, if we can compare it to another section like equations of motion or mechanical energy, for example. So the total linear momentum of an isolated system remains constant. This is either a 0 or 2 mark answer, all or nothing as far as the way that we get marks for this answer. Okay, at this stage we are on 5.2. Calculate the 5.2.1 velocity of car A before the collision. Okay, so this was before the collision, the initial. This was after the collision. So we need the velocity of the car. We have our formulas up here. So the one that we want to work with is this guy over here, because we are just isolating it. We are working with one of the momentums, not the change in momentum. So we can just go ahead, write this formula down and solve for the velocity of the car. So P equals mv. This is our momentum. They've given us the momentum over here, and they have taken right as the positive direction, which means if anything is going to the left, that'll be a negative. So we can write 30,000 over here. Cool. Our mass of car A is 2,000 kilograms over here, and the velocity, the initial velocity, is what we want. So we can just go ahead and divide both sides by 2,000, and our answer for the initial velocity is 15 meters per second to the -1. Right. Okay, so we went 30,000 divided by 2,000, and this was our final answer for the initial velocity of the car before the collision. We're on 5.2.2 over here. It is asking us to calculate the mass of car B for 4 marks. So 5.2.1 was just using the momentum formula, but 5.2.2 has to do with the principle of conservation of linear momentum. What we want to look at when something is 4 marks, it means we're looking at the momentum before and our momentum afterwards. So what this means is that we need to add up the 2 different objects before the collision, accounting for their mass multiplied by their velocity, and this mass multiplied by this velocity. So this is car A over here, and this is car B. This is the before scenario. I will erase some of this just now. So this is before the mass and velocity of car A plus the mass and velocity of car B. We're going to equate that to the mass and velocity of car A after the collision and the mass and velocity of car B after the collision. At this stage, we would have enough variables for everything else but the mass of car B, as that will be the missing factor on both sides. And then we can go ahead and solve for that. So that means I'm just going to write the mv plus mv over here, and then we can start to isolate it. Reminder, this is before, this is afterwards, and this is car A, this is car B. Okay, so car A's mass is 2,000, we know this, and its initial velocity before is 15 meters per second. That is what we calculated just now in 5.2.1. So we have the momentum, the mass times velocity of car A. Now we need to add the mass times velocity of car B. The mass of car B is what we want. We don't have that. And its initial velocity is 0. A reminder that it said collided with a stationary car B. So it was initially 0 before these two cars bumped into each other. So this was A before, this was B before, this is A afterwards, and this is B afterwards. So we have the befores, and now the afterwards is what we need. So the mass of car A after the collision is still the same. So we have 2000 over there, but the velocity we don't have up here. But just like this previous question, we can calculate it considering we have the momentum after the collision. So we can just quickly go ahead and change this previous formula. Okay, so we just quickly changed this formula, which means our momentum after the collision is 10,000, also to the right, which means it is a positive 10,000. And then the mass of the car is still 2000 over there. And now we are going to get the final velocity. And if we go ahead and divide these two things, we get 5 meters per second to the -1 right. And then we can go ahead and plug the 5 in here on the right side of our equation, as we now have the velocity of car A after the collision. And then at this stage, we are on car B after the collision. Car B's mass is still what we want over here, but its velocity was given to us. It says after the collision, car B moves to the right, also positive direction like these guys, to the right, with a speed of 20 meters per second to the -1. So at this stage, we have plugged in everything that we need to in order to solve for m here, as this m over here multiplied by 0 will just be 0 and disappear. So we can go ahead and simplify this. 2000 multiplied by 15 is 30,000 over there. This disappears. 2000 multiplied by 5 is 10,000 over there. And then m multiplied by 20 is just 20m. Okay, we can take the 10,000 over. So 30,000 minus 10,000 is 20,000, and that equals 20m. And then 20,000 divided by 20 is 1,000 kilograms. And that is the mass of car B. So we just earned 4 marks over there. So we're on 5.3. It says draw a labeled vector diagram showing the magnitude and direction of the change in momentum of car A. So car A is what they had over here, is what they plotted here with its momentum and momentum. Change in momentum is our delta P over here, which means it is the final momentum minus the initial momentum. So that means we're dealing with delta P. We have 10,000 because that is our final momentum going right, minus 30,000 also going right, which means we have -20,000 kg dot m dot s to the -1. So that is the magnitude. And if the change in momentum is negative, it means it is going to the left, because it was going fast this way to the right, but then it slowed down, still going right, which means this change in momentum opposed the initial direction that it was going. So that means we have a line going to the left, and we just have 20,000 kg dot m dot s to the -1 over there. That is our magnitude, that is our direction, and this is our final answer, earning us 2 marks. Cool. And then 5.4 says calculate the magnitude of the net force that car A exerts on car B. So we're just looking at car A here, and the net force is this formula up here. It is our F net delta T equals our change in P, our change in momentum over there. Okay, so we are going to use this formula here, so I'm just going to write it down so long. So F net is what we want, so we do not have that yet. Delta T over here was given to us. It was 0.5 seconds. That's what they said up here. The collision lasted 0.5 seconds, so we can just plug that in over here. And then delta P is what we calculated previously, but we can just go ahead and write that again. So it is the change in momentum, which means it is the final momentum minus the initial momentum. So it is 10,000 minus 30,000 over there. So then we can just solve for this. 10,000 minus 30,000 is minus 20,000 as we had already. And then we can divide by the 0.5 over there, leaving our F net as the only thing on the left side. And that means our final answer for F net is minus 40,000 newtons, which just means it is 40,000 newtons to the left, considering negative is to the left, but they only asked for the magnitude, not the direction. So we can just leave our answer here and we are done with this question. So we just earned 3 marks over there. Okay, so 5.5, the last question of this section. It is a theory question, and it says, use the impulse momentum theorem to explain how an airbag, which inflates between the driver and the steering wheel of a car during a collision, protects the driver. So this is 3 marks, and it has to do with that last formula that we were using for 5.4. So I'm just going to rewrite this formula down here. We are given this formula on our formula sheet, and if we go ahead and manipulate the formula, so we take our delta t to the bottom over there, so it is delta p divided by delta t, we can then start to interpret this question a lot easier. Because what happens in a car crash, just like we have been working through in this scenario here, is that there is a large amount of force applied during a car crash, and that large amount of force can cause a lot of damage or injury to the driver. So an airbag is given in a scenario like this to increase the contact time, which helps protect the driver. So the bigger the number we have at the bottom, if we increase the time, the smaller the force applied, which means there is less impact, less force on the driver, and therefore less damage done to the driver. So all that we need to know is that our F net is inversely proportional to delta t. Therefore, the airbag increases contact time and therefore decreases the F net. And that would earn us 3 marks, showing that we understood that an increase in the contact time decreases the F net and therefore protects the driver during a collision. So that is our final answer over there for 5.5, and that is the whole section on momentum and impulse. Cool. So if work, energy, and power is getting a bit confusing, we're about to break down question 6, where we're going to clarify some things like the difference between non-conservative and conservative forces, how to use energy principles, as well as calculating power, and then drawing and interpreting some free body diagrams. So let's jump right in. So question 6 says a 20 kg box is initially at rest, okay, at point Y on a rough horizontal surface, okay, that's also important. The box is pulled to the right by a constant force of 100 newtons over here, parallel to the surface. The box is moved a horizontal distance of 4 meters over here and experiences a frictional force of 65 newtons. Okay, great. So we have all that information, and 6.1 says define the term non-conservative force for 2 marks. So we have 2 types of forces. We have non-conservative and we have conservative. Okay, and the difference between the two is that conserve means that something remains the same, which means conservative force happens regardless of the path taken, which means gravity, for example, is always a conservative force because it does not depend on how far the object travels. Gravity will always act with the same amount of force regardless. But a non-conservative force, for example, is something like friction, because the more we move an object across a surface, the more friction is applied to the object. So if we just move this object a little bit to the right, only so much friction will occur. But if we move it a lot more to the right, more friction will occur. So a non-conservative force is a force for which work done in moving an object between 2 points depends on the path taken. Okay, so that just earned us 2 marks over there. This is an all or nothing question. We either get 0 or we get 2. But the important thing for understanding is that a non-conservative force depends on the path taken. As we mentioned, the more we move the block, the more work done by the frictional force will occur. Okay, so that leads us to 6.2 over here, where they are asking us to name the non-conservative force or forces acting on the 20 kg box for 2 marks. So whenever we're looking for a non-conservative force, we are looking in the direction of movement. And this definition helps us see that because the 2 things that are affecting it as it moves are the applied force or the tension and the frictional force, because both of those will affect how much work is done as the object moves 4 meters. So we can just go ahead and write that down. So we have our kinetic frictional force and the applied force. So that just earned us 2 marks over there. And then 6.3, it says using energy principles only in capital letters, calculate the speed of the box at point Z over here. Okay, so whenever energy principles are mentioned, we have to look at either of these guys. This WNC is a great one because that means the work for a non-conservative force, which is exactly what we're dealing with here. So we can work with this, the change in kinetic energy plus the change in potential energy. So that's great. We can work with that. But one reason we don't have to work with that is because there is no potential energy, because this object is on the ground the whole time. So we don't necessarily need to work with that if we don't want to. The other option we can work with is our W net equals change in kinetic energy, because it is on the ground the whole time, which means there's only kinetic energy, which means we can just go ahead and plug this in as well. Okay, so I'm going to write this formula down for us, and then we can start working with it and seeing what we have. Okay, so we've just written it down, and we're seeing that 6.1 helped us with 6.2, and 6.2 is helping us with 6.3, because the two forces that are contributing to the work done in the system is the applied force and the frictional force. We don't have to look at the normal force and gravitational force. There also aren't any other angles to work with, which means we just have two forces that we're working with. So W net means the resultant work done, which means we have to look at this formula up here and deal with the work done for the applied force and the work done for the frictional force. Once we have that, those two added up or subtracting from one another, considering they're going in different directions, will then equate to the W net. Okay, so we can just write WFA and W frictional force. And then delta EK means the change in kinetic energy, which means half mvf squared. That's our final velocity minus the half mvi squared. Cool. So at this stage, a reminder that W is up here. So I'm just going to write this here for us. So we have F delta X cos of theta. So this is the formula. W represents this. So we're going to plug this in over there and over there. So the applied force has a force in newtons of 100. And then delta X, what we're looking at is the speed of the box at point Z, which means it traveled 4 meters. Delta X is our displacement, which means we multiply that by 4. And then cos is what we write. And then the angle, we either have 0 degrees, which means we're working in the direction of the force. If we put cos 0 in our calculator, we get an answer of positive 1, which just means that this object is going to be moving forward and has a positive direction. So we just write cos 0 here as the applied force is working in the same direction that the object is moving in. We always add up our works. We don't try and subtract them from each other. That is where our cos theta comes in, because the only other option we have is a 180. If we make cos 180, it becomes -1 according to our trig graphs for cos. And then making that 180 makes this whole answer negative, which means that this work, the frictional force, opposes the work done by the applied force, which means they are just going to subtract one another, and we are going to have a smaller net work done. So that means if we are plugging in the F over there for our force, for the frictional force, they told us it has a frictional force of 65 newtons. So we have that over there. And then the distance is the same, considering the frictional force is moving for 4 meters as well. And the only other different thing here, like we chatted about, is the fact that it is cos 180, because the frictional force is opposing the direction of the applied force. So right now we have our two different components for the work, and then we can work on the right side of our equal sign here, which means we have half the mass of the object is 20 kgs. So we have that. The final velocity is what we want. So we do not know that. So Vf squared is what we want. And then once again, half our mass is 20. And then our initial velocity is 0, because the box was initially at rest before the applied force started, which means we have a 0 over there. And this whole thing on the right of our minus sign is going to become 0. Okay, so at this stage, we can go ahead and start to simplify everything. And then we can solve for our final velocity at point Z. So 100 multiplied by 4 is 400. Cos 0 just means 1, so it is still just positive 400. Okay, plus 65 multiplied by 4 is 260, but the cos 180 makes it a negative. So we have negative 260 over there. And then a half times 20 is 10. Vf squared remains over there. And then a reminder that this whole thing amounts to 0 because we are multiplying by a 0 here, considering the velocity was 0 because the box was at rest. So then 400 minus 260 is 140 over there, and this equals 10 Vf squared. Cool. We can divide the 140 by 10, and that leaves us with 14, and that equals Vf squared. And then we can go ahead, take the square root of both, and our final answer for Vf, our final velocity at point Z, is 3,74 meters per second to the -1. So we just earned 5 marks over there. And then 6.4 over here says calculate the average power dissipated by the 100 Newton force between point Y and point Z. So it is just focusing on the 100 Newton applied force, and they're asking for the average power. So if we look up here, we have our PAV equals force times VAV. So we're going to go ahead and write that down. It is the easiest power formula to work with in this case, considering they said average power, and we also have been given the force that we need to work with. So I'm going to write that down now, which means we do not have to look at the frictional force here. We just have to look at the power of the 100 Newton force. So our F is 100 over there. Our VAV is the average velocity, okay? Which means we have to add up the two velocities and then divide them by 2, which means our initial velocity was 0 because it was at rest, and our final velocity is what we just calculated, which was 3.74 over here. So at this stage we have everything. This is only a 3-mark question, which means we can just plug this in our calculator and solve for it, which means our average power is 187 watts, and that is our final answer there for 3 marks. Okay, great. So 6.5 says the box is now pulled upwards by a 100 Newton force on the original surface, which is now inclined at an angle as shown in the diagram below. So everything is exactly the same except this box is now on a slope. So 6.5.1 says draw a labeled free body diagram showing all the conservative forces acting on the 20 kilogram box. So a reminder to the beginning of the lesson when we were talking about the difference between a non-conservative and a conservative force. A reminder that a conservative force stays the same regardless of path taken, which means it is always constant, and the thing that is always constant is gravity. So if we are drawing a free body diagram of the conservative force or forces acting on the box, the only one we have in this situation is our gravitational force over there, and that would earn us 2 marks, 1 mark for the arrow, 1 mark for the label. And then last question, 6.5.2, will the box still have the same speed after 4 meters as in question 6.3? Will it still have the 3.74 meters per second to the -1 at point Z after 4 meters on the slope, or will it be different now that it is on a slope? Write only yes or no, give a reason for the answer. So considering this is on a slope now, there is one other thing to consider, and that is that even though we have the frictional force still working against the direction of the applied force, we also have the FG parallel working down the slope. And because there's an FG parallel working against the applied force, because we are on a slope, it means that the FG parallel will also contribute negatively to the net work done on this whole block. And that means that if we were to plug it back into the formula that we are working with in 6.3, although we would have to work with the potential energy considering there is now height here, it would lose work because of this FG parallel. Okay, and because of that, that would affect the final velocity as it approaches and reaches point Z over here. So will the box still have the same speed after 4 meters as in question 6.3? Our answer is no, and that is because our F net will decrease because FG parallel is negative and will remove energy from the system, i.e. velocity will decrease. Okay, and that just earned us 2 marks over there and 16 marks for this whole section. Cool. So if Doppler is getting a bit confusing, we're about to break down question 7 so that we can see how to approach it, understand the Doppler effect, and how to link it to the formula as well as the application of the formula itself. So it is quite a small section, so let's jump right in. So question 7 says a hawk emits a sound at a frequency of 90 hertz. The speed of sound in air is taken as 340 meters per second to the -1. 7.1 says state the Doppler effect in words. So this one is quite a weird one as far as the wording, but if we rewrite this formula here, we can help link it to the formula. So I'm just going to write down the formula so long. So we have the formula here. We have the frequency of the listener. This equals the velocity of the medium plus or minus the velocity of the listener divided by the velocity of the medium plus or minus the velocity of the source. And this is all multiplied by the frequency of the source. Okay, and with that being said, let's write down the Doppler effect, because the Doppler effect is the change in frequency. So it is the change in frequency, the difference between the frequency of the source and the frequency of the listener, detected by a listener, because the source and the listener, so the source and the listener have different velocities, this guy and this guy, they have different velocities relative to the medium of sound propagation. And the medium of sound propagation is just whether it is traveling through air or through water or through steel, and the speed of sound through that medium. So all this means is that because two different objects are moving relative to each other, the frequency experienced by the listener might be more or less than the source. So for this example, we have a hawk emitting a frequency, but if it is flying towards us, we will hear a higher pitch, like an ambulance if it is driving towards you. But if it is flying away from us, it might be emitting a frequency of 90 hertz, but we will hear it as a lower frequency because it is flying away from us. So this is the change in frequency, the difference in frequency detected by a listener, because the source and the listener have different velocities, are moving either towards or away from each other. That is where the plus and the minus comes in, relative to the medium of sound propagation. We are just adding or subtracting the velocity of the listener and the source from the speed of sound in air or in water, depending on which medium we are listening in. Okay, so that is the Doppler effect in words, and that has just earned us 2 marks over there. Quite a weird phrasing, but if we can link it to the formula, it makes it a lot easier for us to understand the words and what is happening here. Cool. 7.2 says a stationary observer, okay, so this person has no velocity, hears the sound at 88 hertz. Is the hawk flying towards or away from the observer? So this is what we were discussing just now. The fact that the hawk actually emits a frequency of 90 hertz, but the stationary observer hears it at a lower frequency, a lower sound. The hawk is then therefore flying away, because if it was flying towards, we would hear it as a higher pitch. So our answer here for 1 mark, this question is just helping us set up the correct plus and minus signs in 7.3 in our formula here. For 1 mark over here, we just have to say away. Cool. So we just earned 1 mark over there. So 7.3 over here says calculate the speed at which the hawk is flying. So this is 5 marks. We get 1 mark for writing this formula down. So just off the bat, we earned 1 mark over there. And then we can go ahead and plug in all the values here and then solve for the speed of the source over here, considering the source is the thing emitting the frequency. So the frequency that the listener perceives is 88 over here, because that is the frequency that the observer is hearing. The velocity of the medium that was given to us as 340 meters per second to the -1. And now we need to see, is there a velocity of the listener? The listener was stationary, which means we can add or subtract 0. It doesn't matter whether it's a positive or a negative, because the listener is stationary. Okay, and then once again, the velocity of the medium is 340 because that was given to us. And then the velocity of the source is plus Vs over there. And the reason we make this a plus and not a minus is because the source is flying away, which means we are going to have a bigger value at the bottom. Dividing by a bigger number at the bottom will make the frequency that the listener perceives smaller than the frequency of the sound source, because the sound source frequency is 90 over here. But what we can see is that the source is 90, but the perceived frequency is 88, which means we have to divide by a bigger number here in order to get a smaller number here, because the frequency the listener perceives is indirectly proportional to the velocity of the source. So if we subtract this answer will end up being bigger because of the ratio here of 340 over whatever is at the bottom here. So if we end up adding this, we are taking 340 divided by, let's say, 350, for example. Then we have 0.95, for example, and then 0.95 multiplied by 90 will give us 88. But that is the reason we have to add the velocity of the source at the bottom and not subtract it. Considering we have 2 options here, we can either add it or we can subtract it. So a nice way to double check that is to see whether this is directly proportional to the listener or not, and to see whether this will make this value smaller by increasing it, or whether if we subtract it, it will make this guy bigger because we are dividing by a smaller number. At this stage, we have plugged this in. We want to solve the VS, and then once again we're multiplying the frequency of the source by 90 over there. So we can just go ahead and simplify some things. So we can take our 90 over and divide it, so we can have 88 divided by 90 over here, and then 340 plus 0 is 340, and then 340 plus VS is still at the bottom there. We can then go ahead and cross multiply, so we can take the 340 plus VS to the top, we can multiply the 90 up to join the 340, and then we can bring this 88 down to the bottom to divide the 340 and the 90. So we took these two guys up top left, we took the 90 up top right, and we took the 88 down bottom. So we now at this stage can take the 340 over, so we have 340 multiplied by 90 divided by 88, subtracting 340 over here. And then at this stage we have VS left by itself on the left side, and we can just plug this into our calculator and we will have our final answer for the velocity of the source. And our final answer is 7,73 meters per second to the -1. Cool. So that just earned us 5 marks for 7.3 and 8 marks for this whole section. Hey grade 12s, so if electrostatics is a bit confusing, or if it's been a while since we've last done it, we're about to work through question 8, so we can break down the structure of the paper, revise Coulomb's law, as well as electric field at a point, and the relationship between the electrostatic force and the charge. So question 8 says 3 point charges A, B, and C are placed as shown in the diagram below. So we have A here with -5 times 10 to the -6 coulombs, B is +2 times 10 to the -6 coulombs, and then C over here is +7 times 10 to the -6 coulombs. Cool, we have the distance here between A and B, and we do not have the distance between A and C. So that is most likely going to be a question coming up. So then 8.1 says state Coulomb's law in words. So what we have is this that we can help link the words to. So I'm just going to write it down so long. So this formula here, this is the electrostatic force. This is the charge of Q1, the charge of Q2, and the distance between them squared, always measured in meters. K over here is on our formula sheet. It is one of the constants that is given, and its value is 9,0 times 10 to the 9. So Coulomb's law is this guy first. It is the magnitude of the electrostatic force exerted by one point charge Q1 on another point charge Q2 is directly proportional to the product of the magnitude of the charges, the fact that these two charges are multiplying one another, and is inversely proportional to the square of the distance r between them. So that is Coulomb's law, and that is how we link it to the formula, seeing that we start with the magnitude of the electrostatic force over here exerted by one point charge on another point charge. 2 is over here, is directly proportional, is this 3 over here, to the product of the magnitude of the charges, and then 4 over here is inversely proportional to the square of the distance between them. So that just earned us 2 marks over there, and is telling us that we are going to use this formula in the next question. So then 8.2 says the net force on charge A over here due to the charges B and C is 0.866 newtons. Okay, it says calculate the distance D as indicated in the sketch above. So we need to make this statement true, and over here they said the net force, which is very important, which means it isn't just this formula once. What we're doing is this formula twice, because we have the net force over here. So we have to do this formula once for B on A, and then this formula again for C on A, and then equate them to the 0.866 newtons. So we'll set that up over here. And then only one other thing to keep in mind as we set this up is that these guys are not working in the same linear plane. It's not like C is over here and they're just playing a game of tug of war over A, for example. What is happening is that our resultant force is our hypotenuse over here, which means we're actually working with this in terms of Pythagoras. So our equation, we're setting it up very similarly to how we would if they were in a straight line, but we're just working with the fact that our F net is 0.866 over here for the hypotenuse, which means when we plug that in, we just have to use squared values, because that is how we work with our Pythag formula. So what we have is F net squared equals FA on C squared plus FA on B squared, which means this this is A on C over here, and this is A on B over there. These are the two sides of our right angle triangle, and then our F net squared is our hypotenuse. Okay, so we have this set up here. We just need to write this formula in full because we get 1 mark for that. So we still have our F net squared, and then what we need to do is plug in these symbols here as far as K remains the same. And then for A and C, we have QA over here, and then we have QC over there, and then this is over R squared, and then we're going to add the same thing. We have K here, we have our Q of A, and we have our Q of B, and then this is also over R squared. And then now that we have this and just earned 1 mark, we can go ahead and plug in our values over here. So our F net is 0,866 squared. Our K is what we have on our constant sheet, that is 9,0 times 10 to the 9. Our QA over here is -5, but we don't have to plug in the negative into these formulas, considering this negative is being attracted to this positive, this B over here, and this negative is also being attracted to this 7 over here, which means we can ignore it because they're both being attracted. And either way, considering we're going to square this whole formula here, it means we do not have to insert the negative there because ultimately it is going to end up positive. So when we plug in our QA, we can just plug it in as 5 times 10 to the -6. The -6 has to remain, but the negative in front of the 5, that can go away. Cool. And then our C value is 7 times 10 to the -6 over there. And then when we plug in our R in this case is D, that is the distance that we want. And then we must just remember to square that as well. Then we're going to do the same thing over here with this formula, plugging in our K value, our constant, and then our QA, we have that over here. That is our 5 times 10 to the -6, just as we did in this calculation. Cool. And then QB is 2 times 10 to the -6. So we can just sub that in. And then this is all over our R, our distance, our 0,5 over there. And it is measured in meters, so we do not have to do a conversion. And then we just have to square that. And then one thing we haven't done yet is putting the square over everything because we are doing Pythag. And in this setup over here, we just earned another 3 marks, 1 mark over here, 1 mark over here, and another mark over here. So we've earned 4 marks for this 5-mark question, which means we just have to go ahead and solve for D, and then we will have our final answer. Cool. And then at this stage, it looks like we might be able to drop the squareds, but we can't do that. I explored that option, and that answer does not take us to the same answer that we have on the memo, which means we have to work with the squareds here. So we have to square all the values that are just numbers first, which means the 0,866 squared is 0,749956. And then what we can do is we can simplify this whole thing, considering they're just numbers here, and then take it over and subtract it on this side. So we are just left with this on the right side. So this whole thing simplified in our calculator is 0,1296. So I just plugged this all in my calculator with the square, and I took it over to subtract it from the 0,866 squared. So we have these two guys, this guy and this whole guy on the left side now of our equal to sign. And then on this side of our equal sign, we have 9,0 times 10 to the 9 multiplied by 5 times 10 to the -6 multiplied by 7 times 10 to the -6 over d squared to the power of 2, the whole bracket. So I'm just going to rewrite that for us quickly. Okay, so we can just go ahead and simplify the left side so long, and 0,749956 minus 0,1296 is 0,620356. We don't round at this stage, we only round right at the end. And then on this right side over here, considering there's a variable that we have in here, that is the reason we couldn't drop the square initially. So what we have to do is multiply the top and then square it, and then the d squared, we're just going to multiply by 2, considering any variables with the power of 2, we multiply. Okay, and all of those multiplied and then squared equals 0,099225. And then our d squared, that is also getting the square, becomes d to the power of 4. At this stage, we're almost done. All we have to do is take our d to the power of 4 up top. We're just cross multiplying. So that is now in our numerator on the left side, and then bringing our 0,620356 down to the denominator on the right side. And we still have the 0,099225 left on the top right. So we can just go ahead, simplify this in our calculator, and the answer that we have here is 0,1599 ... and that equals d to the power of 4, which means our last move is taking the fourth root of both of these on our calculator, and our final answer for D is 0.63 meters. So that just earned us 5 marks over there. Okay, and then 8.3 over here says charge C is now removed. Okay, so this guy is gone. Point P is 0.2 meters to the right of charge B. So we have charge A, the same charge as we did here. Charge B remains, C is now gone, and now we are looking at point P to the right of both of these charges. So 8.3.1 says define electric field at a point. So electric field at a point, the definition works with this formula over here. So I'm just going to rewrite it for us, which means the electric field at a point. So it starts off with the words that they give us for the definition. So we have the electric field at a point is the electrostatic force. So it is, the equal sign here is the electrostatic force, the F over there, experienced per unit. So per means divide, positive charge placed at that point. Cool. And the fact that it is a positive charge, so charge is our Q over here. The positive helps us orient ourselves when we do question 8.3.3 because the P is a positive charge over here. It is a positive speck of dust, and that helps us relate as to whether the B is repelling it or attracting it, and whether A is repelling it or attracting it when we do the magnitude of the net electric field. So that part is just important when it comes to another calculation, but this just earned us 2 marks, and that is how we link the words to this formula over here. And then 8.3.2, it says draw a labeled vector diagram of the electric field at point P as a result of charges A and B. So as we were just talking about, charge P over here is a positive speck of dust. It doesn't attract like these charges up here. It doesn't have an actual charge that it emits, but it is a positive speck of dust, which is helping us see how it relates to A and B. By that I mean A is a negative charge, right? So A is negative and P is a positive speck of dust, which means A is trying to attract P over here. So these two guys are attracting, but then over here B is positive and P is positive, which means B is repelling P over there. And the fact that B is a lot closer to P than A has the biggest impact because our formula when we are looking at our electric field, I'll write it down quickly. Our formula when we're working with electric field has an R squared, and the fact that the R is squared means the distance has the biggest impact on the electric field at a point, more so than the charge. So the fact that P is being repelled by B quite significantly and A is only attracting P with less pull, our resultant vector diagram is something like this. So we have our E net there. It is the difference between B and A, considering B is repelling P with more of an impact and A is attracting P with less of an impact, which means our E net is going slightly to the right, and that is our final answer there for 2 marks. And a nice way to think about it is imagining that P is a ball floating in a pool and B over here is splashing water away so that P repels, and then A is trying to paddle water towards it to try and bring P towards A. So that is just a nice analogy that works for some of my students to help us visualize this a bit better. The fact that B is splashing water away from P, therefore repelling it, and A is trying to paddle water towards it to bring the tennis ball P towards it. But considering it is further away, it is harder for it to paddle water towards it in order to actually affect P. So then we have 8.3.2. We're now on 8.3.3, and 8.3.3 says calculate the magnitude, the amount of the net electric field. So our E over here. So we focus on electric for the E. Our force is our F over there. So the net electric field, net as well, at point P. Cool. So this is 4 marks, and we're going to write the formula that we're working with. Okay, so we have our E net, considering they said the net electric field, and that is what we drew over here, considering they are minusing each other. 8.3.2 helped us see we are subtracting the electric field of A on P from the electric field of B on P. So this vector diagram helped us see that, and what we can't do is try and equate them on one equation. We can't put Q1 and Q2 on the same equation like our force over there. We have to treat it separately by writing KQ over R squared. This will be our QB on point P. The fact that it is 0.2 meters, we have to treat that separately. So this is equation 1, and A on P is equation 2, which means we are subtracting that from this guy. So we're going to write this here. We have our K. It is the same constant that we had in our previous question for 8.2. And then our Q over here is our QA, and that is over R squared. That distance over there is the 0,5 meters plus the 0,2 meters. The fact that the R's given are in meters is good for us, considering the R's here in this section are always measured in meters. So we don't have to do any conversions. And then also the fact that we have a minus here, it means when we plug our QA in, we do not have to plug in the negative there as well. We don't want to double up. What we want to do is put the minus outside and then just put the actual value for it, ignoring the negative in front of the 5. So our E net is what we want. Our K on our constant sheet is 9,0 times 10 to the 9. Our Q of B is 2 times 10 to the negative 6. And our distance between them is 0,2 meters squared. And then we're subtracting. K again is 9 times 10 to the 9 over there. Our QA is just 5 times 10 to the negative 6 over here. Cool. And we do not have to put the negative, otherwise we're going to double up our negative in front that we've already dealt with. And then that is over R squared, and that is 0,5 plus 0,2, which is 0,7 squared. So at this stage, we just earned 1 mark for this setup of the equation, and then another 2 marks for plugging in here correctly and plugging in here correctly. Our 4th mark would just be to put all of this in our calculator and get our final answer for our E net, which means I'm just going to go ahead and do that on my end, and our final answer for our E net is 358,163,27. Cool, quite a large number. And then our units are n.c to the negative 1. Relating back to our initial formula where we got the definition, where we have F over Q, which is newtons over coulombs. So this is our final answer here for 8.3.3, earning us 4 marks. And then 8.3.4 over here is a theory question. It says if point P, this point over here, was between charges A and B, so if point P was between charges A and B, the net electric field would never be equal to 0 at any point. Explain the validity of this statement. So is it true or false? That is 1 mark, and then why is the 2nd mark. So P is a positive charge over here, and what happens is this negative is attracting this positive point charge to the left, and this positive is repelling this positive point charge that way, which means that no matter what, whether it is right in the middle or a little bit here or a little bit there, these two guys are on the same tug of war team, the same team as far as pulling the water towards it to bring the ball towards it and splashing the water away from it to move the ball away from it. These guys aren't fighting for it. They're not fighting in opposite directions. That can equate to 0. They are working on the same team in the same direction, which means that regardless of where it is put in between A and B, it can never amount to 0 because they are working in the same direction. So is this statement true or false? This statement is true because it would never be equal to 0. So we have true because the E net is always added, EA plus EB, and these two charges are working in the same direction. So 1 mark for true, 1 mark for our explanation, and that just earned us 2 marks. And then 8.4 over here, it says the relationship between the electrostatic force and a charge is illustrated in the graph below. During this experiment, the second charge and the distance between the two charges are kept constant. So we could ignore the second charge and we can ignore the distance. So we have the electrostatic force charge graph. We have our electrostatic force on our y-axis. That is our dependent variable. We have our charge times 10 to the negative 6 coulombs. So we have our microcoulombs over there. On our x-axis, that is our independent variable. And what we can see is that it is a perfectly straight line. So then 8.4.1 says, what mathematical relationship between the electrostatic force and the charge can be deduced from the graph? So it is only 1 mark, and it is talking about the fact that it is going from 0 all the way up in a perfectly straight line, which means it is just a directly proportional relationship. And that would earn us 1 mark over there, just saying directly proportional. And then last question for this section, 8.4.2 says, use the information in the graph to calculate the magnitude of the electric field, the E, around the charge when it experiences a force of 0,005 newtons. So 0,005 is over there and 0,005 is over there. This is 3 marks and we are getting the electric field. So we're just just going to rewrite this formula here. E equals F over Q. We don't have to work with E equals KQ over R squared because the other charge is kept constant and they are kept an equal distance away from each other, which means we can ignore this formula and just write this formula over here. So we have E equals F over Q. So that is option 1, or we can do a gradient formula because as we'll see, our gradient formula is exactly the same. Our change in Y is our electrostatic force here, taking it from there down to 0. And our change in X over here is the same thing, taking our charge from that point all the way down to 0. So our gradient formula, whenever it comes to graph questions, will usually be the exact same as our formulas, which means we can choose either option over here, but we can just work with option 1, plugging in our F and our Q based on the graph. So 0,005 newtons is what we're working with for our force, and then our charge over there is 1 times by 10 to the negative 6. Just don't forget the 10 to the negative 6 over there. So we can write that in, and our final answer is 5,000 newtons per coulomb to the negative 1. And that just earned us 3 marks for the last question and 21 marks for the whole section. Hey grade 12s, so if electric circuits is a bit confusing or if it's been a while since we've done it, we're about to break down question 9, the last question of the June 2025 physics paper. So let's jump right in. So question 9 over here says circuit A and circuit B, so A and B, are connected as shown below. In both circuits, the same battery, exactly the same battery is used, and all resistors are identical with a resistance of 3 ohms each. Very important. So that guy's 3 ohms, 3 ohms, 3 ohms. Same thing here. Each resistor is 3 ohms, just in different combinations here. The battery has an EMF and internal resistance of unknown values, and voltmeter and ammeter readings are indicated in the diagrams below. So we have a voltmeter reading of 3.6 volts over here and 2.4 amps over there in this circuit, and then voltmeter reading of 7.56 volts over here and ammeter reading of 1.26 over there. So there are different voltmeter and ammeter readings because the resistors are in different arrangements. So then 9.1 over here says define power for 2 marks. So we can go up to our formula sheet and we can see our formulas for power. Our P over here is power, and that is measured in watts, and then our W is our energy measured in joules. And the fact that we have all of our power formulas, the first power formula is where we get our definition from, because P equals W over change in T means that power is the rate, the delta T, at which work, our W, work is done. And that just earned us 2 marks over there. This is an all or nothing question. We either get 2 marks or we get 0. But with that, it means we are probably going to have a question on power coming up next. So 9.2 says for circuit A. So we're just looking over here. 9.2.1, what would be the current through resistor R2? So R2, if we zoom in a bit, that is this guy over here. So we want one of the resistors in parallel. Okay, so what would the current be through resistor R2? So considering it is 2 marks, it means it isn't a calculation. A 3-mark question has a calculation, but what is important is referencing a note we're going to make that helps us remember the relationship for voltage and current in series and parallel. So we have our series circuit, and series current is the same, but our voltage is different. What this means is that in a series circuit, so circuit B, same amount of current over here over R1, same amount of current over R2, and the same amount of current over R3. But the voltage then is different. The voltage is split, which means the voltage over R1, the voltage over R2, and the voltage over R3 adds up to the total voltage in our circuit. And then in a parallel circuit, these guys are swapped, which means our current is different, or it splits, and our voltage is the same in each branch. So our current is different for a parallel section, which means it splits in proportion to the resistances that each resistor has. But our voltage will be the same on each branch. So a nice way to think about it that helps some of my students is that we are on a slide, for example, and voltage is the amount of tennis balls we have on top of a slide. The current is the speed at which the tennis balls flow down the slide, and then the resistance is whether there is sandpaper on the slide or how much sandpaper is on the slide to slow it down. Okay, so if we're just looking in series over here, it means our current is the same. It means the speed at which it goes over this resistor and that resistor and that resistor at the same speed. But our voltage is different because different tennis balls are being caught on different resistors at different times. And that is why in series, the current is the same. The speed at which it goes over all of these different pieces of sandpaper is the same, but the voltage where each tennis ball gets caught up on each resistor is different. And that is why that works for series. But in parallel, we have two different slides with the same amount of tennis balls, which means our voltage is the same because the tennis balls split over both sides. We do not get more tennis balls because we introduce a parallel section. So our tennis balls, half of them go this way, half of them go that way. And that is why our voltage is the same. But our current is different because there might be a different amount of resistance on each parallel branch of our slides, which means that the tennis balls might move here a little bit quicker than they move here, considering there might be more resistance on this parallel section compared to this parallel section, and current is the speed at which the tennis balls flow. Okay, so let me know if that analogy helps, because they asked 9.2.1 what would be the current through resistor R2. So R2, R3, and R1. So our note is telling us parallel, our current is different. Okay, which means that it isn't 2.4 amps like this guy. But what is important is that we know that this is a 3 ohm resistor, this is a 3 ohm resistor, and this is a 3 ohm resistor, which means our analogy in this case is that there is the same amount of resistance in both cases. So our current is 2.4 amps over here, and our current is different according to our note in parallel, but there is the same amount of resistance on this branch and this branch, which means it is different from the total amount, but it is split perfectly in half, which means we have 1,2 amps over there and 1,2 amps over there. We have in our series portion, we have the full 2,4 amps over here, but as we move to the parallel section from positive to negative, we get half of it going this way and half of it going that way because there is exactly the same amount of resistance on each branch. So that is why this is a 2-mark question, because all we have to do is halve our 2.4 amps and our final answer is 1,2 amps through resistor R2. So that just earned us 2 marks over there. Cool. And then 9.2.2 over here says calculate the power dissipated by both R2 and R3. Okay, so if we were measuring power, let's call this guy P over there, it is over both R2 and R3. So we have a couple options for power formulas, referencing our note to see which values we have to work with. So our easiest formula to work with is probably our P equals V times I over there. So I'm just going to write that down for us along. So power is what we want. The voltage for this parallel branch is 3,6 collectively, because just like I've drawn this P over here, imagine our voltmeter that is in the middle is actually situated here. What this is telling us is that this is the collective additive amount of voltage over both R2 and R3 over here. So whether it is right in the middle or whether it is over here, it is treated exactly the same. This 3.6 isn't for R2 and then R3 separately. They aren't over just a branch of the parallel chain. They are over both of them. So if we drew it over here, connecting from outside the whole parallel section, it would be interpreted exactly the same as the 3.6 over here, which means our voltage in this case is 3,6 volts, because what this is doing, it is working with the voltage for the parallel section after we have already squished the two different resistors together. After we've already done our resistance in parallel calculation, getting the effective resistance of the parallel branch, which means we have our voltage, and that is why when it comes to the current over here, we don't use the 1,2 over each branch, because the current over here is the total 2,4 amps over there. It is the total 2,4 amps going over the whole effective parallel section. It is the 1,2 plus the 1,2 over there. And that is why it helps us to visualize it a bit easier if our voltmeter is outside and not right in between, because we think it might be for this parallel branch or that parallel branch, or treat them individually, but it is accounting for the whole parallel branch already calculated using this calculation and getting the effective resistance as if there was just one resistor there the whole time. So let me know in the comments below if that makes sense. Otherwise, there are other options on the memo with other calculations over here that we can work with, provided we are taking the correct values based off of our notes and whether current is the same or different, or whether voltage is different or the same based on how we interpret this. But what we have here then is 3,6 multiplied by 2,4, and we can just work that out in our calculator, and our final answer for the power dissipated by both R2 and R3 is 8,64 watts, and that just earned us 3 marks over there. And then 9.3 over here says for circuit B, so circuit B over here, 9.3.1, calculate the energy measured in joules, so that is our work, used for resistor R1, so R1 over here. If the current flows for 10 minutes. So we have to work with time. So if we go and look at our formulas, we have to see which formulas we can work with that have time. So our energy is somewhere over here. It is our W, which means the only 3 formulas with time are these guys. And they are talking about R1 specifically, which means we have the resistance there. So let's look for a formula with resistance. We either have this last one or this second last one over there. But I like the fact that we have the current in a series circuit, which according to our note is exactly the same. So I'm going to go ahead and work with the second last formula over here. So I'm going to write that down so long for us, but you can choose either formula, whatever you feel most comfortable with, and whatever correct path you see first. So our I is what we have here. We also have the voltage. That's why we could have gone with the other formula, but then we would just have to account for the fact that the voltage is split over these two guys. So we could have done that, but over here, our current is the full 1,26 amps over this resistor, because our current is the same in series and these are all in series. So we have 1,26 squared. The resistor that we are working with is just over R1 over there, so it is 3 ohms, which they mentioned all of the resistors are 3 ohms each. And then time, delta T, although they gave it to us in minutes, we have to work with seconds, so we're just going to multiply the 10 minutes by 60 to turn it into seconds. And then at this stage we can just go ahead and plug all of this in our calculator, and then we will have an answer. And our final answer for the amount of work is 2857,68, and this is measured in J, this is measured in joules. So that just earned us 3 marks over there. And then 9.3.2, it is a theory question, and it says, how would the currents be affected if R1 over here burnt out and was not removed? Okay, they love this question. So the fact that it burnt out and was not removed, okay, how'd that affect the current, right? Only increases, decreases, or remains the same. 1 mark for the correct choice there, and then give a reason for the answer is our second mark. So if this resistor burnt out and was not removed, it means that our currents will decrease. The reason it decreases is because current can now no longer flow from this positive to this negative terminal. Although it might look like it can flow and bypass this resistor by flowing on this parallel branch here where the voltmeter is, the voltmeter has such a high resistance that it won't allow the current to flow and pass through, which means that because this is burnt out, our positive terminal is no longer connected to our negative terminal, and that means our circuit is not complete. And if our circuit is not complete, there will no longer be any current flow. So we said decrease, that gave us, or decreases, right, exactly what they told us to write for 1 mark. And then our reason is because voltmeters have such high resistance, therefore no current can flow in circuit via the alternate pathway. Okay, which means it won't let any current pass through, and that is the reason that it would decrease. Great job, guys. So that just earned us 2 marks over there. And now 9.4 says define the term EMF for 2 marks. So another definition that is going to lead into some sort of question using the EMF formula. So defining the term EMF. So our EMF formula is over here. It's our EMF equals I multiplied by the external resistance plus the internal resistance. But there isn't a nice way to link the formula to this equation, but there is a nice way to link the formula to our equation here. Our W equals V times Q. So I'm going to rewrite that down for us, because this, once we rearrange it, is our voltage formula. And EMF is almost the same as voltage or potential difference. It is just in the battery. So I'm going to write that down for us now. W equals V times Q, and then if we take our Q over, we have W over Q equals V, and EMF is just the potential difference inside the battery, which means that it is the maximum work done, okay, is our W, by a battery. That is pointing to the fact that our EMF is inside the battery itself, not in the external circuit, which means it is the maximum work done by a battery per unit charge, and that is our Q over here passing through it. and that just earned us 2 marks over there, and it is an all or nothing question. We either get 2 or 0. There are no half marks for this question, and that is how we link it to this formula here, just remembering that it is inside the battery specifically and not in the external circuit. And last question for this section and the whole paper, following on from the EMF definition, 9.5 says resistor R1 is replaced by a new 3 ohm resistor. So it is no longer burnt out there anymore, and it is replaced with the exact same resistance as it initially had, the 3 ohm resistors throughout. So now it's saying calculate the value of the EMF, follow-on question, and the internal resistance of the battery used in circuit A and circuit B. Okay, so this is a 6-mark question. We do not have the EMF there, and we do not have the internal resistance there and there. Okay, so 2 unknowns, and the way that we approach something when there are 2 unknowns is a simultaneous equation. They did this question for the final 2025 physics exam, and it can be a bit confusing, so it's good that we are seeing it now before that. So the fact that it is more than 5 marks means it is a simultaneous equation where we are going to equate not the W equals VQ. It's not about that formula. That was just for the definition. We are going to equate 2 different formulas for our EMF equals I bracket external resistance plus internal resistance. And then we can go ahead and solve for them. Okay, so I'm just going to go ahead and write that down twice for us. Cool. And this is the equation for circuit A, and this is the equation for circuit B. The reason we can once again do a simultaneous equation is because it has the same EMF and internal resistance for both. They said that up here in the initial writing, which means it is the same battery used on both sides. So that means our EMF is what we're going to leave, as well as the internal resistance, because we're going to make this EMF equal that EMF and then solve for the internal resistance when we equate these 2 equations, and then plug that back in to get the EMF in either one of these formulas, which means in circuit A, EMF remains and our current is 2.4 amps over there. So we have 2.4 amps over there because that current was in series, which means it was the current for the whole circuit. Our external resistance we'll have to calculate because we have a resistor in series and then 2 resistors in parallel. So we're going to have to add up the resistors in parallel separately and then add them to the resistor in series so that we have the total external resistance for this circuit. So that means our R tot over there equals RS plus RP. And then our RS over here was our 3 ohm resistor, and our effective resistance in parallel we have to calculate first. So we're going to use this formula up here, 1 over RP equals 1 over R1 plus 1 over R2, so that we can figure out these 2 guys and their effective resistance for this parallel branch. So that means over here we have 1 over RP equals 1 over R1 plus 1 over R2, and then both of those resistors were 3 ohms each. So when we add them up, we have 2 over 3, but that is 1 over RP over there, which means we just have to go ahead and flip both sides, which means we have 3 over 2 for our resistance in parallel, which adds up to 1.5 ohms over there. So we can then just go ahead and plug that 1.5 in our formula over here, because that is the effective resistance, the total resistance for the parallel branch. And that means our total resistance here is 4.5 ohms for the whole circuit, including the series and the parallel branch added up together. So from there, we can plug in the 4.5 over here by our capital R, the external resistance, and then we want to plus little r because we are trying to solve that in the next step. And then we're going to do the same thing here for circuit B. Our EMF we do not have yet. Our current in series for the circuit is 1,26 over there. So we have the current in series, and then our external resistance, this is just a circuit that is entirely in series. So we just have to add up the 3 resistors in series, which means we have 3 plus 3 plus 3, which means our total resistance is 9 over here. So there's no parallel branch. We don't have to do anything like that. We just have to add them up normally. So then we have plus 9 over there, and little r is what we want. So at this stage, we have our 2 equations. We want to make this EMF equal that EMF. So what we're left with is bringing this guy down and making it equal this guy. So we have 2,4 multiplied by 4,5 plus r equals 1,26 multiplied by 9 plus r over there. At this stage, we've just earned 4 marks, 1 mark for our formula, 1 mark for setting both of them up, another mark for equating them. And now we need to go ahead and solve for R and then solve for the EMF. Okay, so at this stage, we can just FOIL this 2.4 into both of these terms here and FOIL this 1.26 into both of those terms over there. So 2.4 multiplied by 4.5 is 10.8 over there. And then 2.4 multiplied by R is 2.4 R. And that equals 1,26 multiplied by 9 is 11,34 plus 1,26 multiplied by R is 1,26 R. So then we can go ahead and take our R's to one side. So 2,4 R is our biggest R. So it's easiest to take the 1,26 R over that side. So 2,4 R minus 1,26 R is 1,14 R over there. And then this 11,34 is the biggest one. So 11,34 minus 10,8 is 0,54 over there. So we took the like terms to each side, and now we can just divide by the 1,14 over here and divide by this 1,14 over there. And that means our final internal resistance is 0,47 ohms over there. And now that we have that, we have the little r that we can plug into either one of these formulas, either circuit A or circuit B, considering the resistance will be the same in both. So we can just go ahead and write down circuit A, plugging in our little r, our internal resistance there. So that means EMF is what we want. I'm rewriting circuit A over here, which means we have 2,4 over there multiplied by 4,5 plus by the internal resistance that we just calculated plus 0,47 over there. And then we can just go ahead, plug this in our calculator and earn our final mark for this question. And our final answer over here equals 11,94 volts. So if we plug in the 0,47, we end up with 11,93 or 11,92. But if we keep our previous answer unrounded and plug it into this final answer, we then get 11,94, which is what the memo says, which means that even though we are rounding our R off here, plug in the unrounded answer into your final equation so that you can then round the EMF off to 2 decimal places correctly as well. And that is our EMF and our final answer for this whole question. We just earned 6 marks there, 20 marks for this whole section, and 150 marks for this whole paper, completing the June 2025 physics paper. Very well done, guys. Great job. Let me know if there are any questions in the comments below, and otherwise I will see you in the next video where we look at the chemistry June 2025 paper.